and get my whiteboard up. Okay, so let me remind everyone kind of what we were doing last time. First of all, we have these master equations, which are split into delta x equations, and there's only one of them really. The second one, v final x equals v initial x, you can kind of just remember as a concept, although that equation does appear on your equation sheet. And then in the y direction, we have for y components, delta y equals v initial y times t plus 1/2 ay t squared, and vfy equals viy plus ayt, and finally vfy squared equals viy squared plus 2ay delta y. Okay, so those are the equations we had, and basically they're the same equations you were working on in chapter 2. So in a sense, chapter 3 is just reinforcing and building on what we learned in chapter 2. And we had one additional equation that we derived, which is called the range equation, and it's useful enough that I include it on our equation sheet, and you can just use this directly when you're solving problems as long as it's appropriate for that situation. And you know, if you recall, what it is appropriate for is when we have something that starts and stops at the same level. And we want to find the horizontal range, which normally we call that delta x, but I guess to help us remember that this is only valid in a special situation. Instead of calling it delta x, a lot of books call it r. So today we are scheduled to just practice reading textbook problems, interpreting them, solving them. So like in principle, this is all bonus material because we've learned conceptually everything that we need to learn. But you know, more examples is always better than less examples. So we'll just get some more practice, but really remember, me practicing is not what you need. It's you practicing that you need. And I've already practiced a lot. So these examples hopefully will help you, you know, tackle problems when you're working on them. And remember also that you should try to do these problems without looking at the solutions. That's really what's going to help you, you know, get there the fastest. So we're going to be doing problems from the 3000 Problems book. And we are starting with problem 5.9. Now, a few people have emailed me through the first couple of chapters having trouble finding problems. And so the problem 5.9, that is not the same as 5.90. That is, we don't find 5.9 after 5.89. We find 5.9 after 5.8. So that's on problem 77. And it says, a body is projected from the ground at an angle 30 degrees with the horizontal at an initial speed of 128 feet per second. So first of all, I don't know why someone is shooting a body into the air, but here comes the body. And the initial speed is 128 feet per second. Notice the units are different than what we're used to. And this angle, it says it's from the ground, so I'm you know, ignore the fact that the body's a little bit above the ground here. Okay, so that's what happens. And ignore air friction, which we are going to ignore air friction in every single problem in this chapter. A, in how many seconds will it strike the ground? So we have V initial equals 128 feet per second. Theta equals 30 degrees. AX equals 0 and AY equals negative G. That comes from it being in the air and ignoring friction. And then we want to know T equals question mark. How many seconds before it strikes the ground? So to say strikes the ground, we would say delta Y equals 0. So this is part A. And part B says, how high does it go? So I'm going to write this as Y max equals question mark instead of delta Y equals question mark, because delta Y equals 0 for the whole flight, but they're asking a separate question, which is how high does it go later? So I'm going to label that in my picture, and we'll come back to it and figure out how to interpret it more carefully. And part C says, what is its range? So C says R equals question mark. Okay, so let me comment on a few things before we get started. They gave us weird units. Okay, they gave us feet, and we have two options. One is to look up the conversion factor between feet and meters and change this V initial into meters per second. The other is we can look up the value of G in feet per second squared instead of meters per second squared. So I picked this problem because I like the problem, but I don't particularly like the units. It's just that I assigned to you guys most of the problems that use meters already. So let me just tell you that G in the units, in the English units, is 32 feet per second squared. So we'll just kind of keep this number in mind for any problems we do today that use feet instead of meters. But on your contest, all of our problems will use meters. Okay, we won't do any problems with feet. But it doesn't really matter what the units are because our solution strategy is to solve without even plugging numbers in. Second of all, we have V initial and theta, and almost the first thing we want to do every time is take that information about the initial velocity that's in the polar form and turn it into the Cartesian or complete form. So we could say Vix equals Vi cosine of theta, and Viy equals Vi sine of theta. And I'm just going to leave it at that because we can always plug in numbers later. That's another good thing about not using numbers. If you use numbers, every problem seems totally different because they have different numbers. But if you use symbols, every single time Vix is Vi cosine of theta and Viy is Vi sine of theta. So you can build up sort of a memory more quickly. Okay, so let's go for part A first. Any questions about the setup? No questions? Okay, so we want to find time, and we want to find the time when delta Y equals 0. So let's look at up here at our equations for time. One of them involves us knowing the range. Now that would be a valid strategy if we would solve part C first and get the range and then solve for time. Totally reasonable. Or we can look in the Y equations and we have two equations that have time. Hopefully we're getting enough experience by now to recognize that the first equation looks pretty good because I know delta Y and I know VIY in principle and I know AY. And the second equation is not so good because I don't know VFY, but it would work if in a pinch. So I'm going to pick equation number 1 on the Y direction. Delta Y equals VIY T minus G over 2T squared. So I'm already sort of putting in that the AY is negative G. And I can even go ahead and add in that VIY is VI sine of theta. And we can check what we know. We know delta y is 0, and we know VIY, that's given. We know theta, that's given. We know the g, and I'm noticing here that when I wrote this line, I forgot the t, so probably some of you also noticed that. I should have a t after the VI sine of theta. So we can clearly solve this for t. And we do that just by factoring out t. That gives me t times the quantity VI sine of theta minus g over 2 times t. And this is going to be solved if either t equals 0 or this whole expression equals 0. And again, why do we get two answers? Because we're solving the question, at what time is delta y 0? In other words, when is this thing on the ground? It's on the ground twice. Or thing, it's not a thing, it's a body, it's a person. Maybe it's a person. I'm actually joking about body. I think they just mean an object. I don't think they mean a body. But the body is on the ground at the beginning and at the end. So this one is at the beginning. That's clearly not the one we want. We want this one, the end. So we just set that expression VI sine of theta minus g over 2t equal to 0. And a little bit of algebra gives us VI sine of theta equals g over 2t. And that's going to give us t. By multiplying both sides by 2 and dividing by g, we get 2 VI sine of theta over g. So we have an expression for the time. And we can plug in our numbers for that. Let's go to the next page. And if I put in my numbers with, let's see, I think it was 128. Yes, 128 feet per second times sine of 30 degrees. And then we just divide by the value of g in the units of feet, which is 32 feet per second squared. We can see the feet are going to cancel out. So we should get a time in seconds. And it looks like that is going to be 4 seconds. Okay. Any questions about that? Danielle.
So when you plugged in the negative 2t squared, can you explain that when you had delta y equals the initial yt minus g over 2t squared?
Why did I put minus g over 2?
Yeah.
So we have ay. It should be really plus 1/2 ay t squared. But my ay is equal to negative g. So I'm really kind of replacing the ay with negative g. So that would be a 1/2 times minus g times t squared. And then I like to put the g on top of the 1/2, kind of mix it into the fraction.
Okay, thanks.
Does that make sense? Okay.
Yeah.
Okay. So, okay, good. You know, something I've noticed about the online class versus face-to-face class is in the online class, people are much more reluctant to ask questions. So I really do appreciate questions like that, Danielle. And, you know, you guys shouldn't be shy. I know you know, you gotta turn on your mic and, you know, but really you'll learn more if you ask questions, and the other students will also learn more when you ask questions. So, you know, just ask questions. Blair.
Yeah, I have a question. Could we
Okay,
have
great.
just used the quadratic formula and put 0 in for C and gotten the same thing, or no?
Absolutely. Yes, you
Okay,
can
that
use
would
the
have worked
quadratic
too.
formula. It would work. Yep, it absolutely works. So if you feel more comfortable with the quadratic formula than factoring, you can
Yeah.
totally do that.
Okay,
Yeah,
that's just like
absolutely.
how I was doing it in the homework, and then you did it that way, but I figured I would have got the same answer.
Yeah,
Okay, thank you.
you would for sure. So you would, if we go back and look, um, let's see, we would have, okay, so minus g over 2t squared plus vi sine of theta t. So if you, you know, call this a and this is b, you're going to get t equals negative vi sine of theta plus or minus a square root of minus vi sine of theta squared over 2 times minus g over 2. So what happens on the top is these things, if we, they're basically the same, because the square root of something squared is just, you know, that thing. So you get minus vi sine of theta plus or minus vi sine of theta over negative g. So why I'm going through and showing this is you've seen it in your work, but other students will see. What happens here is if I pick the plus sign, I just get 0, which, remember, 0 was one of my answers, but it's not the one I want. If I pick the plus sign, I just get 0, and if I pick the minus sign, this thing just doubles, and I get minus 2 v initial sine of theta over minus g, which is, you know, the same as what we had here, 2 vi sine of theta over g. So yeah, absolutely. You'll get the same thing either way.
Okay, thank you.
Sure. Okay, so that was part A, to find the time. Part B said, let's find Y max. So there's a lot of ways we can handle this. One way would be to reason that if the whole trip takes 4 seconds, it should only take 2 seconds to reach the top. Now that's actually good logic, but we've never proven that before, so I wouldn't use it yet because we haven't seen that that is true. It makes sense that it's true, but it wouldn't be true if there's air resistance, for example. But if there's no air resistance, it is true the time on the way up is equal to the time on the way down if it goes the same distance up as down. But another way we could do it is just solve for the time when we're at the top. That's what we've already been doing in chapter 2. And who remembers how we would say that we're at the top in chapter 2? How did we express being at the top mathematically? We had problems like that, like the balloon. How high does the coin go? How do we determine that highest point? No one remembers that? Grace?
Oops. The VF equals 0 for that.
Yeah, exactly. We would say that the final velocity was 0. Now, it's a little different here because our velocity vector is sort of doing something like that. Was there another hand? Someone else have a hand? So in this case, if I see this velocity vector at the top, what can I say about it? It's not that it's the velocity itself is 0, but there's something about it that's 0. Anyone have an idea? So what's different about this velocity when it's at the top is that it's perfectly horizontal, right? It's not going up yet anymore. It's not going down yet. It's perfectly horizontal. And if I have a perfectly horizontal vector, and remember, vectors kind of live on their own axes. A horizontal vector just lives on the x-axis, which means it does not have a y component. So when we go to part B, we want to find delta y when v final y equals 0. Not the whole v final, but just its y component. Its x component never goes away. It just stays the same all the way across the pattern. So if this is what we are doing, then we can just look at our y equations, and we have v final y squared equals v initial y squared plus 2 ay delta y, where here we're solving for delta y, and we know that at the top, vfy is 0. We also know viy and ay. So we can solve it for vy pretty easily. That's going to be minus viy squared equals minus 2g y. So here again, I'm replacing the ay with a minus g. So it looks like I'm just replacing it with g, but then there's also a minus in front. And then we can divide both sides by negative 2g. So delta y is going to be minus viy squared over minus 2g. And notice for this, I didn't even need to use anything about the x direction. The y direction alone is enough for me to solve this problem, which is pretty cool. So time of flight only cares about not time of flight. The max height only cares about the y direction. So that's true for time of flight as well. And when I put in, so we can see that the minus signs cancel. And when I put in VIY is VI sine of theta, what happens when I square it is I have to square the VI, but I also have to square the sine of theta. So this is a notation you may not be so familiar with, like squaring a trig function. But if I square a trig function, I put the square on the function sine, not on the theta, because I don't want to accidentally think that I'm supposed to square the angle. So what sine squared of theta means is you find the sine of theta and then you square that number. So this is my formula for delta y, and in this case it's going to be 128 squared sine squared of 30 over 2 times 32. And I get 64. And because we're working in English units, this y is not in feet, in meters, it's in feet. So 64 feet high. It's nice of them to pick a nice number like 128 so that we get nice numbers for our other things. 128 is nice because it's a multiple of 32. Okay, any questions about part B? Okay, finally part C said find the range. So we have a range equation. It says VI squared over G times the sine of 2 theta. By the way, let me just quickly go back. Hopefully you plugged this in on your calculator on your own just to sort of make sure your syntax is correct. But when I do sine squared of 30, just to stress it again, on my calculator, I'm finding the sine of 30, which is 0.5, and then I'm squaring that number. Okay, so on your calculator, depending on your model, you may just find the sine of 30 and then square that number, or your calculator may have something, a display that looks a little If it's a more expensive calculator, you can actually type it looks a little bit more like this. Okay, now going back to the range equation, my VI is 128, so 128 squared over 32 times the sine of 2 times 30. So that means the sine of 60 on my calculator. And that is 21. I don't think that's right. Let me try that number again. Yeah, that number was not right. So 443.4 feet. So I'm allowed to use the range equation because the picture looks like our original soccer ball on a level field picture. The object, the body, starts on the ground and ends on the ground. Mathematically, if I see delta y equals 0, that means I can use the range equation. Okay, and if I don't have delta y equals 0, then I cannot use the range equation. All right, does anyone have any questions about parts A, B, or C of this problem? No? Okay, let's do a new problem. So we're going to do number 5.10. Okay, so again, problem numbers in physics textbooks, this is not 5.1. You don't drop the 0. This is sort of telling you chapter 5, problem 10. Okay, so that problem says that a hose lying on the ground shoots a stream of water upward at an angle of 40 degrees to the horizontal. So we have, I would recommend drawing a picture. So you have a hose or a snake or something, and it sprays water upward at an angle, which means we have an initial velocity at a certain angle of 40 degrees. The speed of the water is 20 meters per second, so VI equals 20 meters per second as it leaves the hose. How high up will it strike a wall which is 8 meters away? So here's a wall that is a distance of 8 meters away, and the path the water follows, I'm going to use a different color for that path. Now, let me show you how not to draw the path. Don't draw the path like that. Okay, let me say a few more words before I erase that. Don't even draw that on your notes. But it's asking how high up we go. So delta y, I want to know delta y, and I know delta x, and I know this angle. And the reason I don't want to draw the picture like this is because this line, although it's bent a little bit, it still kind of looks like there's a triangle here. And what I don't want to do is I don't want to think that tangent of 40 degrees is delta y over delta x, opposite over adjacent, because this does not form a triangle. The triangle would be if this line would keep going straight. And then this distance here we could find using the tangent of 40. But I don't want that distance. Okay, I do not want that distance. So let me go back and undo that. So how do I want to draw it? I want to draw it very curvy. Okay, something like that. If I have to cheat and make this angle extra big so that I can draw a curvy line, I'll do it. Now, the real line could very well do something like that. It could be still going on its way up when it hits the wall. If this is a high pressure hose, it might do that. But I don't want to draw it like that, because if I do, I'm likely to make an assumption. Just visually, it will trick me. Okay, I've just seen that mistake and even made that mistake myself so many times. I'm trying to warn you against it. So we want to find delta y, which is, you know, just the way I drew it, a short distance. But I don't really know if delta y is short or big. I'm not making an assumption there. I'm just drawing a picture. I don't want to assume it's 0. So now let's translate. We have VI equals 20 meters per second, and theta equals 40 degrees. Delta X equals 8 meters. Delta Y equals question mark. AX equals 0, and AY equals negative G. That's 6 of my 9 variables. And the variables that have not been mentioned yet, which has been a kind of a common theme in a lot of the problems, it's not universal, but it is common, that we don't say anything about VFX or VFY or T in the problem statement. So this is what's been given. And we know that we're going to immediately use VI and theta to find VIX, which is VI cosine of theta, and VIY, which is VI sine of theta. So how do I solve for delta y? Once I translate, I look at what I'm solving for, and that's where I start. I want to start with one of my 2 equations that has delta y. And if we go back and look at those master equations, delta y is in the first y equation and in the third y equation. And in principle, I can pick either one, but what looks the best, which one looks the best to you? I'll give you a poll. Do you like equation 1 or equation 3? Okay, which equation do you want to use? Equation 1 or equation 3? I don't want to use any equation because I'm tired and sick of this is not an option. So you have to pick option 1 or option 3. Okay, so most people, maybe 2 to 1, agree on using equation 1. Now equation 3 will also work. I picked equation 1. I like it a little better, but either one works. The right equation is the one that you choose because it's going to work. So let me, my page is not the right shape. Delta y equals v initial y t plus 1/2 ay t squared. And I'm going to put in that VIY is VI times the sine of theta, and AY is negative G. And let's see what we know. We know VI, and we know theta, and we know G, but we do not know T. So we have to solve for T. How do I solve for t? Well, I have two options. The x equation, delta x equals vixt, or the second y equation, v final y equals v initial y plus ayt. So I'm going to do another poll. See, this is, you didn't know it, but physics is democratic. So we'll just decide this democratically. I'm asking, are we going to pick the x equation, delta x, or the y equation, vfy? Which one do you like the best for solving this? Oh, you guys are good. You guys are good. I like that one the best too. Okay, so we're going to use delta, let's keep it red, delta x equals vixt, which is vi cosine of theta t, and that means t equals vi cosine of theta over delta x. And we have numbers. We have numbers for vi, theta, and delta x. So that is what we want to use. So we can bring our delta y equation down. I'm just going to continue it onto the next column. And we have delta y equals vi. You know what? I'm just going to go to the next page because this is going to be a big, nasty equation. So delta y equals vi sine of theta t minus g over 2 t squared, where t we decide was equal to delta x over vi sine of theta. So we plug that in. So where those parentheses are, I'm going to plug in my expression for t. That is delta x over vi sine of theta. Delta x over vi sine of theta. And boy, I do not envy you if you have not been working with symbols in your homework, because if you haven't been working with symbols, this looks crazy. Okay, this looks insane, like you just are ready to drop the class before I even take a break. But if you've been working with symbols, it should still look a little crazy, but it shouldn't scare you. Okay, so let's see what happens when I plug all this stuff in. Some things are going to simplify. I think, sorry, this should have been a cosine of theta. Darn it, I should have looked back at the other page before I started writing. Let's check that. So yes, we had vi cosine of theta over, wait, I messed this up too. I'm sorry about that. It should have been, wait, it should have been what sorry. So this, when I divide both sides by vi cosine of theta, we have delta x over vi cosine of theta. So delta x over vi cosine of theta is what I have here. Okay, I apologize if you're taking notes, which you should be taking notes instead of just watching. I just totally ruined your notes. Okay, so what happens when we try to simplify this? Well, the first thing I would say is that the VI's cancel out on this first piece. The second thing is that we have a sine of theta over cosine of theta. And there's a trig fact about sine over cosine that you may or may not know. I'm going to guess most of you don't know it. But it turns out that sine of theta over cosine of theta is equal to tangent of theta. Okay? Sine of theta cosine equals tangent. How do we know that? Because sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. And if I write that as a ratio, I can cancel the h's. And I get O over A, which is the tangent. Okay, so if you never saw that before, in fact, just a tip for you, if you're ever struggling with a problem because you have sines or cosines or tangents and you don't know what to do, call them O over H, A over H, or O over A, and start canceling O's and A's and H's, whatever, and you probably will solve the problem. Okay, so back to our expression. Then we have minus G over 2 times delta X squared over VI squared cosine squared of theta. So let me rewrite this in the most simple form. And this equation that I'm coming up with here, this is not an equation I would memorize. It's not one that you're going to use in problems, but it is one that you may see in solutions to other problems because they may take the easy way out and say, well, we'll use this equation. You should not do that. You should work problems out from the master equations. But if you see this and you're wondering where it comes from, what this equation is an equation of y versus x. This is basically the mathematical formula that shows you the parabola, the parabolic shape of the trajectory. The time has been removed. And so if you pick a value of x, it will tell you a value of y, and that just gives you sort of a curve. So the shape of that curve, y versus x. This is not the x versus t graph. This is actually like a photograph of the path. And now we can put in our numbers. We have 8 meters times the tangent of, what was our angle, 40 degrees, minus 4.9, that's G over 2 is 4.9, times 8 over 20 squared cosine squared of 40. So this is, maybe even a challenging number to get on your calculator without making a mistake. So go ahead and try it on your calculator and see if you can get it. Oops, it should be 8 squared. 8 squared on top. I got 6.14 meters. If anyone else gets that, let me know. Second time I got it, I got 5 point, what did I get? 5.38. So if anyone got that number, let me know. And I'm going to try it a third time. Third time's a charm. I got this number twice. Anybody get a number yet?
I keep getting like less than 1.
Less than 1? Anybody getting less
Definitely
than
doing it wrong though.
Okay. Anybody else getting something like that? Less than 1?
I got 5.36.
Okay, that's pretty close to what I got. Anybody else get 5.36? $5.38. Okay, let's call it 5.4. And I think this is probably right because I've gotten that several times now. So why is it challenging on the calculator? It has to do with parentheses, and you know what I did is I worked out this number first, and I actually like to get the denominator first and then divide the numerator by the denominator and then multiply by minus 4.9 and then add that number to 8 tangent of 40. That's how I did it. If you try to put it all in one line in your calculator and you don't have perfect parentheses, you can get crazy numbers. So it's worth it to break it down into pieces. Okay, so if we go back and look at the picture, you know, the real picture, the real path probably looks something like that. But again, I don't want to draw it like that because it looks like I have a triangle. And if I tried to say that, you know, tangent of 40 equals delta y over delta x, I would get delta y equals 6.7 meters. So I would be off by not so much that I knew it was wrong, but I would still be off. Okay, any questions about this problem?
I still can't get the answer.
So what I would recommend is break it into pieces. So this bit here, let's see what you get for that. So I get 0.27 for this number. Then times 4.9, or negative 4.9 gives me a negative 1.34. And then 8 times the tangent of 40 is 6.7. So 6.71 minus 1.34.
Okay.
Did you figure out what it was? Was it this piece in the circle?
Yeah, I had a very I had trouble doing that.
Yeah, that's the hard part. So on your calculator, you may want to do something like 8 squared divided by, and then put parentheses, and do 20 squared times cosine squared of 40. But it depends on what kind of calculator you have.
Okay.
Okay. So that's, you know, that's why in class when I'm doing problems and coming up with numbers, it's definitely a good idea to practice with your calculator. Dustin.
If you go up the page back, the whiteboard back,
Mm-hmm.
couldn't we just have figured out time there? And
To get
supplement
a
that?
number?
Correct.
You mean, yeah, absolutely. We can do that, but then we don't get stronger at algebra. So you're right. If we want to just get the number, we can do that. If we want to have a result, this could be a useful result, and I wanted you to see this result because you'll see it in some solutions. But honestly, if I'm working on a contest problem, I would just get a number. But when I'm doing homework. I do all of this algebra to just, it's like a mental workout, just to get myself into good shape.
Gotcha.
Because, yeah, okay, great.
I just wanted to make sure that I didn't miss something that we needed to go down this road. I get the mental workout, but I just wanted to.
Yeah. Okay, perfect. Haley.
For like the trig identities, how you were saying like sine over cosine is tangent, is that something that we should memorize, or is that something that would like be on our sheet, or would just not even be on the contest?
It should be on the sheet if you might need to use it on the contest.
Okay.
However, it is hard for me to predict, what you'll need, because different people may take different paths on problems. Now, like in this case, you wouldn't really have to use that. You could just plug in sine of 40 divided by cosine of 40, right? You don't actually have to do that. It's just a simplification. Now, I don't know if this will work. I think there was one student, I don't remember who it was, who was logged in to collaborate during the contest. If that was you, let me know. But I believe you can be taking the contest on Respondus and also have Collab open and ask me questions. So I'd like to figure that out on this next contest. But that would be great, because if there's an equation like this one that I didn't anticipate you needing and you discover you need it, I'd like for you to be able to just ask me and I can tell you, if Respondus lets us do that. So maybe I'll try to figure that out before this upcoming contest. But yeah, generally, this is one, I think it's worth knowing this identity, and I typically put it on the exam if I don't expect everyone to know it. So I do put it on if I think you might come across it. Okay, other questions? All right, so we shouldn't probably start a new problem before taking a break. So let's go ahead and take maybe a 5 to 7 minute break, maybe start back exactly at noon, and then we'll keep working. Stopping recording.